Welcome to Science After Dark. Tonight we're drifting into one of the cosmos' most enigmatic mysteries, a force so elusive that we've never directly seen it. Yet without it, every galaxy in the universe would simply fall apart. We're talking about dark matter, the invisible scaffolding that holds everything together, the silent architect that builds the very structures we call home. I hope this journey helps you settle into that peaceful space between curiosity and wonder, where the mind can wander freely through the vastness of space. Before we float into the cosmic darkness together, I'd love to know where you're listening from tonight. Let me know in the comments. I truly am intrigued to find out where you are listening from. Now, settle in and get comfortable. You don't need to remember every detail or take notes. Just let these ideas wash over you like gentle waves, carrying you deeper into the mystery of how darkness itself becomes the foundation for light. Ready? Let's begin our quiet journey into the invisible realm that built everything we see. Picture this. You're standing in your kitchen, watching flour slowly settle into a mixing bowl. The flour doesn't just pile up randomly. It follows the shape of the bowl, creating gentle hills and valleys, forming patterns that mirror the container holding it. Now imagine that the bowl is invisible, completely transparent, and all you can see is the flour taking shape in mid-air, following contours you cannot perceive. That flour is ordinary matter, the stuff of stars and planets and you. And that invisible bowl is dark matter, the mysterious scaffolding that gives structure to everything in the cosmos. This isn't science fiction or wild speculation. This is the quiet reality of how our universe works. Every galaxy, every star, every planet exists because of an invisible framework that we can only detect through its gravitational influence. Dark matter doesn't shine, doesn't emit light, doesn't interact with electromagnetic radiation in any way we can measure. It's like a cosmic ghost, present everywhere yet impossible to see directly. But here's what makes it absolutely essential. Without dark matter, galaxies simply could not exist. The ordinary matter we're familiar with, the protons and electrons that make up stars and planets, would never have been able to clump together into the magnificent spiral arms and elliptical structures we see scattered across the night sky. Dark matter is the foundation upon which the entire visible universe rests. To understand how this invisible architect works its magic, we need to journey back to the very beginning, to a time when the universe was young, hot, and remarkably smooth. About 380,000 years after the Big Bang, the cosmos had cooled enough for the first atoms to form. At this point, the universe was still incredibly uniform, with only tiny density fluctuations. Variations so small, they were like gentle ripples on an otherwise perfectly calm cosmic ocean. But these tiny ripples were everything. They were the seeds from which all structure would eventually grow. And dark matter was already there, already beginning its patient work of construction. You see, dark matter had a crucial advantage over ordinary matter in these early times. While regular matter was still coupled to photons, still interacting with light and radiation in ways that prevented it from clumping together easily, dark matter was free to follow gravity's gentle pull. It didn't get pushed around by radiation pressure. It didn't scatter light or get heated by electromagnetic interactions. It could simply fall inward, following the contours of those primordial density fluctuations. Think of it like this. Imagine two types of dust settling in a room. One type is so light and fine that every breath of air, every movement, every ray of sunlight pushes it around, keeping it suspended and dispersed. The other type is heavier, unaffected by these disturbances, free to settle into patterns determined purely by gravity and the shape of the surfaces below. Dark matter was that second type of dust, settling into the gravitational valleys carved out by those early cosmic ripples. As dark matter began to clump together, it created what cosmologists call dark matter halos. These are vast, roughly spherical clouds of invisible matter, each one potentially containing trillions of times the mass of our Sun. They formed first, before stars, before galaxies, before any of the bright, shining objects we associate with the cosmos. In the darkness of the early universe, invisible structures were already taking shape. But dark matter halos weren't uniform spheres. They had structure, hierarchy, complexity. Smaller halos merged to form larger ones in a cosmic dance of gravitational attraction. Like tributaries flowing into rivers, which then flow into even mightier waterways, dark matter structures grew through countless mergers and accretions, building ever more massive frameworks. Within these dark matter halos, something remarkable began to happen. The ordinary matter, the stuff that would eventually become stars and planets, started to fall inward, drawn by the gravitational wells that dark matter had carved out. This ordinary matter, mostly hydrogen and helium gas left over from the Big Bang, began to collect at the centers of these invisible structures. As the gas fell deeper into the gravitational wells, it began to heat up and compress. Temperature rose, density increased, and eventually, conditions became just right for the first stars to ignite. These weren't the orderly, long-lived stars we see today, but massive, brilliant giants that burned hot and died young, seeding the cosmos with heavier elements through their spectacular deaths. But here's the beautiful part. The dark matter halos didn't just provide a gravitational well for ordinary matter to fall into. They provided protection, stability, and ongoing structure. Without the extended gravitational influence of dark matter, the gas that formed those first stars would have been blown away by stellar winds and supernova explosions. The dark matter halos acted like cosmic nurseries, sheltering the formation of stars and allowing them to accumulate into larger and larger groups. Over hundreds of millions of years, these stellar nurseries evolved into the first galaxies. Small, irregular collections of stars embedded within vast dark matter halos. And as time passed, these proto-galaxies continued to merge and grow, guided always by the invisible hand of dark matter's gravitational influence. The process wasn't random or chaotic. Dark matter's distribution throughout the universe follows what cosmologists call the cosmic web, a vast network of filaments and nodes stretching across billions of light years. Picture a three-dimensional spider's web, with thick strands connecting massive junction points, and thinner threads weaving through the spaces between. Dark matter flows along these filaments like water through a vast irrigation system, channeling matter toward the nodes where galaxy clusters form. This cosmic web isn't something we can see directly, but we can map it through careful observations of how galaxies are distributed across the sky. When we do, we find that galaxies aren't scattered randomly through space. They're organized into vast chains and clusters, separated by enormous voids where very little matter exists at all. This large-scale structure, this cosmic architecture, is the signature of dark matter's invisible influence. Within individual galaxies, dark matter continues to play its essential role. Take our own Milky Way, for example. The visible parts of our galaxy, the stars and gas clouds we can see, extend out about 100,000 light-years from the galactic center. But the dark matter halo that surrounds and permeates our galaxy extends much further, perhaps 300,000 light-years or more. We're living inside a vast, invisible sphere of dark matter, and without it, our galaxy would have torn itself apart long ago. Here's why. Stars in the outer regions of galaxies move fast, very fast. According to the laws of gravity and the amount of visible matter we can see, these outer stars should be moving so quickly that they escape the galaxy entirely, like a ball thrown too hard to stay in orbit around Earth. But they don't escape. They remain bound to the galaxy, moving in stable orbits year after year, century after century. The only explanation that makes sense is that there's much more mass in the galaxy than we can see, mass that provides the extra gravitational pull needed to keep those outer stars from flying away into intergalactic space. That unseen mass is dark matter, comprising about 85% of all the matter in typical galaxies. This isn't just true for our galaxy, It's true for every galaxy we've ever studied. From the smallest dwarf galaxies to the most massive ellipticals, they all show the same pattern. The visible matter alone cannot account for the gravitational forces we observe. There must be vast amounts of invisible matter providing additional gravitational scaffolding. But dark matter does more than just hold galaxies together. It shapes how they form, how they evolve, and how they interact with one another. When galaxies collide, as they sometimes do over cosmic timescales, their dark matter halos merge first, creating the gravitational framework within which the visible matter will eventually settle. The spectacular galaxy mergers we see unfolding over millions of years are really just the visible aftermath of dark matter, halos finding each other and joining together. Even the spiral arms of galaxies like our own Milky Way owe their existence partly to dark matter. The beautiful sweeping curves of stars that define spiral galaxies are density waves, patterns that propagate through the galactic disk like ripples on a pond. These waves are sustained by the complex gravitational interactions between ordinary matter and the dark matter halo that surrounds it. As we peer deeper into space and further back in time, we can actually watch this process of galaxy formation unfolding. The most distant galaxies we can see with our most powerful telescopes appear as they were when the universe was young, still in the early stages of assembly. Many of these ancient galaxies look irregular, chaotic, nothing like the orderly spirals and ellipticals we see in our local cosmic neighborhood. They're still in the process of formation, still being shaped by the gravitational influence of their dark matter scaffolding. And yet, for all its importance, dark matter remains profoundly mysterious. We know it's there because of its gravitational effects. We can map its distribution by observing how it bends light from more distant galaxies, a phenomenon called gravitational lensing. We can watch how it influences the motion of stars and gas within galaxies. But we still don't know what it actually is. Is it made of undiscovered subatomic particles? Is it some exotic form of matter that interacts only through gravity? Could it be something even stranger? Perhaps a manifestation of physics we haven't yet understood? These questions remain open, driving some of the most ambitious experiments and observations in modern science. What we do know is that dark matter is patient, subtle, and absolutely essential. It works not through dramatic explosions or brilliant flashes of light, but through the gentle, persistent pull of gravity. Over millions and billions of years, this invisible force has shaped the architecture of the cosmos, creating the framework within which stars shine, planets form, and life itself becomes possible. In our next segment, we'll explore the intricate dance between dark matter and ordinary matter, and how this cosmic partnership continues to build and reshape galaxies even today, billions of years after the first structures began to form in the ancient darkness of space. Now, let's drift deeper into this cosmic dance, where dark matter and ordinary matter perform their eternal waltz across the stage of space-time. It's a partnership so intricate, so perfectly choreographed, that it continues to surprise astronomers with its elegance and complexity. Imagine you're watching a master sculptor at work, but instead of clay or marble, they're working with gravity itself. Dark matter is that invisible artist, and its medium is the very fabric of space. It doesn't create with hammer and chisel, but with the gentle persistence of gravitational attraction, pulling and shaping over timescales so vast that entire civilizations could rise and fall in what amounts to a single brushstroke. As dark matter halos continue to grow through mergers and accretion, they create what scientists call a hierarchical structure. Small halos merge to form larger ones, which in turn combine to create even more massive structures. It's like watching a cosmic tree grow, with each branch representing a merger event, each leaf a galaxy that will eventually call that dark matter framework home. But this isn't a simple linear process. The growth of dark matter structures is beautifully chaotic, influenced by the initial conditions of the universe, the expansion of space itself, and the complex gravitational interactions between neighboring structures. Some regions of space become dense with dark matter, forming massive galaxy clusters that can contain thousands of individual galaxies. Other regions remain relatively empty, creating vast cosmic voids where very little matter of any kind exists. Within these growing dark matter halos, the ordinary matter begins its own complex journey. As hydrogen and helium gas falls into the gravitational wells created by dark matter, it doesn't simply pile up at the bottom like rocks in a bucket. Instead, it begins to rotate, forming what astronomers call an accretion disk. This rotation is crucial because it determines the eventual shape and structure of the galaxy that will form. The gas spirals inward, heating up as it falls deeper into the gravitational well. But dark matter provides more than just a gravitational container. It also provides stability. Without the extended mass of the dark matter halo, the rotating gas would be much more susceptible to disturbances. Stellar winds from massive stars, shock waves from supernova, and radiation pressure from young, hot stars would all conspire to blow the gas away before it could form new generations of stars. This is where the story becomes even more fascinating. The dark matter halo doesn't just passively hold ordinary matter in place. It actively participates in regulating star formation through a process called feedback. When massive stars explode as supernovae, they inject enormous amounts of energy into the surrounding gas. In a galaxy without a substantial dark matter halo, this energy might blow all the gas out into intergalactic space, effectively ending star formation forever. But in a galaxy embedded within a dark matter halo, something different happens. The halo's gravity is strong enough to retain much of that heated gas, even as it expands and cools. Eventually, the gas settles back down into the galactic disk, ready to form new stars. This creates a self-regulating system where star formation proceeds at a steady pace over billions of years, neither running away in a burst of activity nor shutting down completely. The result is the kind of stable, long-lived galaxy we see around us today. Spiral galaxies like the Milky Way have been forming stars steadily for more than 10 billion years, creating multiple generations of stellar populations, each one enriched with heavier elements forged in the cores of previous generations. This wouldn't be possible without the moderating influence of dark matter. As we observe galaxies at different distances, and therefore at different times in cosmic history, we can actually watch this process unfolding. The most distant galaxies appear smaller, more irregular, and more actively star-forming than nearby galaxies. They're caught in the act of assembly, still growing their dark matter halos, still settling into the stable configurations we see in the local universe. But the influence of dark matter extends beyond individual galaxies. On larger scales, it creates the cosmic web, that vast network of filaments and nodes that spans the entire observable universe. Dark matter flows along these filaments like water through a vast river system, carrying ordinary matter along with it toward the nodes where galaxy clusters form. These galaxy clusters are among the most massive structures in the universe, containing hundreds or thousands of individual galaxies, all bound together by their collective dark matter halos. The clusters themselves sit at the intersections of multiple dark matter filaments, like cities built at the confluence of major rivers. And just as rivers transport nutrients and sediment that nourish the landscapes they flow through, dark matter filaments transport gas and smaller galaxies that feed the growth of these massive cluster galaxies. Within galaxy clusters, we can observe dark matter's influence most dramatically through a phenomenon called gravitational lensing. The immense mass of the cluster, dominated by dark matter, warps the fabric of space-time so severely that it acts like a giant magnifying glass. Light from even more distant galaxies gets bent and distorted as it passes through this gravitational lens, creating multiple images, arcs, and rings of distorted galaxies. By carefully analyzing these lensing effects, astronomers can map the distribution of dark matter within galaxy clusters with remarkable precision. What they find is that dark matter and ordinary matter don't always overlap perfectly. In some cases, particularly when clusters have recently collided with one another, the dark matter and ordinary matter can become separated, each following its own gravitational trajectory through the aftermath of the collision. This separation provides some of the strongest evidence for dark matter's existence as a distinct form of matter rather than simply a modification of our understanding of gravity. During cluster collisions, the ordinary matter, mostly in the form of hot gas, can be slowed down by electromagnetic interactions as the gas clouds ram into each other. But dark matter, interacting only through gravity, passes right through these collisions relatively unaffected, creating a spatial offset between where most of the matter is and where most of the mass appears to be. These collision events also reveal something profound about dark matter's nature. It appears to be nearly collisionless, meaning that dark matter particles can pass through each other with very little interaction. This property allows dark matter to form the smooth, extended halos we observe around galaxies, rather than collapsing into dense, compact objects like ordinary matter does when it forms stars and planets. The nearly collisionless nature of dark matter also helps explain why it can form such large-scale structures. If dark matter particles interacted strongly with each other, they would radiate away energy and collapse into much smaller, denser configurations. Instead, dark matter halos maintain their extended structure over billions of years, providing the stable gravitational scaffolding that galaxies need to form and evolve. But dark matter's influence on galaxy formation isn't uniform across all types of galaxies. Different environments lead to different outcomes, creating the rich diversity of galactic structures we observe today. In dense environments like galaxy clusters, the strong gravitational fields and frequent interactions between galaxies can strip away gas and halt star formation, creating the large, red, elliptical galaxies that dominate cluster cores. In less dense environments, galaxies can grow more peacefully, accumulating gas along dark matter filaments and forming the beautiful spiral structures we associate with galaxies like our own Milky Way. The spiral arms themselves are manifestations of density waves that propagate through the galactic disk, patterns that are sustained by the complex gravitational interplay between the visible matter in the disk and the dark matter halo that surrounds it. Even the smallest galaxies, the dwarf satellites that orbit larger galaxies, owe their existence to dark matter. These tiny galaxies often contain very few stars relative to their total mass, suggesting that they're dominated by dark matter to an even greater degree than larger galaxies. Some of these dwarf galaxies are so faint that they've only recently been discovered, hidden in the outer regions of the Milky Way's dark matter halo like cosmic hermits. The relationship between dark matter and galaxy formation continues to evolve as the universe ages and expands. In the early universe, when everything was closer together and denser, galaxy formation proceeded more rapidly. Dark matter halos grew quickly through frequent mergers, and the gas they contained was compressed and heated to temperatures that triggered intense bursts of star formation. Today, in our older, more expanded universe, the process has slowed considerably. Dark matter halos still grow, but more gradually through the steady accretion of smaller structures rather than dramatic mergers. The gas that feeds star formation is more diffuse and harder to collect, leading to the slower, steadier rates of star formation we observe in present-day galaxies. In the vast cosmic theatre where this drama unfolds, dark matter remains the silent stage manager, invisible to the audience but essential to every scene. Without its patient, persistent influence, there would be no galaxies, no stars, no planets, and ultimately, no observers like ourselves to contemplate the mystery of existence. The universe would be a dark, empty expanse, devoid of the structures that make complexity and life possible. As we continue our journey through this cosmic mystery, we'll next explore how scientists are working to detect and understand dark matter directly, using some of the most sophisticated and sensitive instruments ever devised to catch glimpses of this elusive cosmic architect that has been shaping our universe from the very beginning. The quest to detect dark matter directly is one of the most ambitious undertakings in modern science, a delicate hunt for something that seems determined to remain hidden. It's like trying to catch shadows with a butterfly net, except the shadows are fundamental to the very existence of the net itself. Scientists around the world have built extraordinary machines, buried deep underground or floating in the quiet of space, all designed to glimpse the invisible threads that weave our cosmic tapestry. Picture the most sensitive scales you can imagine, so precise they could detect the weight of a single snowflake landing on a mountain. Now imagine scales 1 billion times more sensitive than that, housed in chambers so quiet and isolated that they make the deepest ocean trenches seem bustling with activity. These are the kinds of instruments physicists have constructed in their patient pursuit of dark matter particles. Deep beneath the Black Hills of South Dakota, nearly a mile underground, sits one such detector. The rock above filters out cosmic rays and other interference, creating a sanctuary of stillness where scientists wait for the rarest of events. The detector itself is a tank of liquid xenon, cooled to temperatures that would make Antarctica feel tropical, monitored by thousands of sensors that can detect the faintest flicker of light or the tiniest vibration. The theory is beautifully simple, even if the execution is extraordinarily complex. If dark matter is made of particles, then occasionally, very occasionally, one of these particles might collide with an atom in the detector. The collision would be incredibly gentle, like a whisper brushing against a feather, but it should produce a tiny flash of light and a minute amount of heat. The challenge is distinguishing this cosmic whisper from all the other whispers, vibrations, and background noise that permeate even the most isolated environments. Other experiments take different approaches, each one a testament to human ingenuity and patience. Some look for the annual variation in dark matter signals as Earth orbits the Sun, carrying us through different regions of our galaxy's dark matter halo. Others search for the products of dark matter annihilation, the possibility that dark matter particles might occasionally collide with each other and produce more familiar particles we can detect. In space, telescopes scan the cosmos for gamma rays that might signal dark matter interactions in the centers of galaxies or in the remnants of smaller galaxies that have been torn apart by gravitational forces. These observations require years of patient data collection, sifting through countless cosmic rays and background radiation to find patterns that might reveal dark matter's hidden signature. The European Research Centre, known as CERN, has taken yet another approach, attempting to create dark matter particles in the most powerful particle accelerator ever built. By smashing protons together at nearly the speed of light, physicists hope to recreate conditions similar to those just after the Big Bang, when dark matter particles might have been created in abundance. The particles themselves would be invisible to the detector, but their presence might be inferred from the energy and momentum that seems to vanish from the collision. Each of these approaches represents decades of theoretical work, engineering innovation, and international collaboration. Teams of scientists from dozens of countries work together, sharing data and insights, all united in their quest to understand this fundamental component of our universe. The experiments themselves are marvels of precision, often requiring technologies that push the boundaries of what's physically possible. Yet despite all this effort, dark matter continues to elude direct detection. The particles, if they exist as discrete entities, interact so weakly with ordinary matter that they pass through our detectors like ghosts through walls. This isn't necessarily a failure of the experiments. It's actually consistent with what we expect from dark matter based on its behavior in galaxies and galaxy clusters. The very properties that make dark matter so effective at building cosmic structures, its apparent inability to interact electromagnetically and its nearly collisionless nature, are the same properties that make it so difficult to detect in laboratory experiments. It's as if dark matter is perfectly designed to be essential yet invisible, present everywhere yet impossible to grasp directly. This ongoing mystery has led some scientists to propose alternative explanations. Perhaps there are no dark matter particles at all. Maybe our understanding of gravity itself is incomplete, and what we interpret as the gravitational effects of invisible matter is actually evidence of modifications to Einstein's theory of relativity on cosmic scales. These alternative theories, collectively known as modified gravity theories, suggest that the force of gravity behaves differently over the vast distances involved in galactic dynamics. Just as Newton's laws needed to be updated by Einstein's relativity to account for extreme speeds and strong gravitational fields, perhaps Einstein's equations need further modification to account for the very weak gravitational fields that exist in the outer regions of galaxies. But modified gravity theories face their own challenges. While they can explain some observations, like the rotation curves of spiral galaxies, they struggle to account for other phenomena, particularly the way dark matter appears to behave during galaxy cluster collisions. The separation of gravitational effects from ordinary matter during these collisions seems to require the presence of additional, invisible mass rather than simply modified gravitational laws. The cosmic microwave background radiation also provides strong support for the dark matter paradigm. The tiny temperature fluctuations in this ancient light carry the imprint of sound waves that propagated through the early universe when it was still hot and dense. The pattern of these fluctuations matches theoretical predictions remarkably well, but only if the universe contains roughly 5 times as much dark matter as ordinary matter. These observations from the very early universe, combined with the evidence from galaxy rotation curves, gravitational lensing, and large-scale structure formation, create a compelling case for dark matter's existence. The consistency of the evidence across such different scales and epochs suggests that we're observing the effects of a genuine cosmic component rather than a systematic error in our understanding. Meanwhile, theoretical physicists continue to explore what dark matter might actually be. The leading candidates are hypothetical particles that arise naturally in extensions of the standard model of particle physics. These particles would have been created in the hot, dense conditions just after the Big Bang, then survived in abundance as the universe cooled and expanded. Some theories suggest dark matter might be made of particles called WIMPs, weakly interacting massive particles, which would occasionally interact with ordinary matter through forces similar to the weak nuclear force. Others propose axions, extraordinarily light particles that were originally postulated to solve a different problem in particle physics, but could also make up dark matter. Still, other theories venture into even more exotic territory, suggesting that dark matter might be composed of particles that exist in hidden sectors of reality, entire families of particles that mirror our own, but interact with us only through gravity. These hidden sector theories open up the possibility of rich, complex dark matter physics that we've barely begun to explore. The search for dark matter has also driven remarkable innovations in detector technology and data analysis techniques. The sensors used in dark matter experiments are among the most sensitive ever created, capable of detecting individual photons or measuring temperature changes smaller than a billionth of a degree. The statistical methods used to analyze the data have applications far beyond particle physics, contributing to advances in fields ranging from medical imaging to climate science. Perhaps most remarkably, the quest to understand dark matter has revealed just how much we still don't know about the universe we inhabit. For all our scientific progress, for all our sophisticated theories and precise measurements, we find ourselves in the position of being unable to directly detect what appears to be the dominant form of matter in the cosmos. This cosmic humility is both frustrating and exhilarating. It reminds us that the universe still holds profound mysteries, that there are fundamental aspects of reality waiting to be discovered. Every negative result from dark matter experiments, every failed detection, actually tells us something important about the nature of these elusive particles. We're gradually constraining their properties, narrowing down the possibilities, closing in on the answer, even when we can't yet grasp it directly. The story of dark matter is still being written, chapter by chapter, experiment by experiment, observation by observation. Each new piece of evidence adds another brushstroke to our portrait of the invisible universe, revealing the hidden architecture that underlies everything we see. And as we continue this patient detective work, we're not just learning about dark matter. We're learning about the fundamental nature of reality itself, about the deep structures that make galaxies possible and life conceivable. In our final exploration, we'll discover how this cosmic mystery continues to shape not just galaxies, but our understanding of the universe's ultimate destiny, as dark matter and its even more mysterious counterpart, dark energy, engage in a cosmic struggle that will determine the fate of everything that exists. As we drift deeper into this cosmic mystery, we encounter an even more perplexing character in our universe's story. While dark matter quietly builds the scaffolding of galaxies, there's another invisible force at work, one that seems to be pulling everything apart just as persistently as dark matter holds it together. This is dark energy, and together with dark matter, it creates a cosmic tension that will ultimately determine whether our universe ends in fire or ice. Imagine the universe as a vast balloon being inflated, but instead of air filling it from within, the balloon itself is stretching, carrying everything stuck to its surface farther and farther apart. That's essentially what dark energy does. It doesn't push galaxies away from each other like some cosmic wind. Instead, it causes space itself to expand, creating more distance between distant objects with each passing moment. This discovery came as one of the greatest surprises in modern astronomy. For decades, scientists expected that the expansion of the universe, which began with the Big Bang, would gradually slow down over time. Gravity, after all, is an attractive force. All that matter in the universe, both ordinary and dark, should be pulling everything back together, putting the brakes on cosmic expansion. But in the late 1990s, two independent teams of astronomers were studying distant supernovae, using these stellar explosions as cosmic lighthouses to measure how fast the universe was expanding at different times in its history. What they found defied all expectations. Instead of slowing down, the expansion of the universe was actually speeding up. Something was overpowering gravity on the largest scales, stretching space itself at an ever-increasing rate. This mysterious force came to be known as dark energy, and it appears to make up about 70% of everything in the universe. Combined with dark matter's 25%, this means that ordinary matter, everything we can see and touch and measure directly, comprises less than 5% of the cosmic inventory. We are living in a universe that is 95% invisible to us. The relationship between dark matter and dark energy creates a fascinating cosmic drama that has been unfolding for billions of years. In the early universe, when everything was much closer together, dark matter dominated. Its gravitational influence was strong enough to overcome dark energy's tendency to stretch space, allowing the first structures to form and grow. Galaxy formation proceeded rapidly during this era, with dark matter halos merging and accumulating ordinary matter at a tremendous pace. But as the universe expanded and matter became more spread out, dark energy began to gain the upper hand. The density of matter decreased as space stretched, but dark energy remained constant, a fixed property of space itself. Eventually, around 5 billion years ago, dark energy became the dominant force in the universe's evolution. This transition marked a turning point in cosmic history. Before this moment, the universe was in what cosmologists call the matter-dominated era, when gravity and dark matter were winning the cosmic tug-of-war. Galaxy formation was robust, structures were growing larger and more complex, and the universe was becoming increasingly organized and structured. After the transition, we entered the dark, energy-dominated era we're living in today. Galaxy formation hasn't stopped entirely, but it has slowed dramatically. The acceleration of cosmic expansion makes it increasingly difficult for new structures to form. Dark matter halos can still grow through mergers, but the overall rate of structure formation has declined significantly. This cosmic competition between dark matter and dark energy plays out differently at different scales. On the scale of individual galaxies and galaxy clusters, dark matter still dominates. These structures are dense enough and bound tightly enough that dark energy has little effect on their internal dynamics. The Milky Way isn't expanding along with the rest of the universe. Neither are galaxy clusters or even the local group of galaxies that includes our own. But on larger scales, dark energy rules supreme. The vast cosmic web of dark matter filaments is gradually being stretched and diluted by cosmic expansion. The spaces between galaxy clusters are growing larger, and eventually these structures will become so isolated that they'll lose contact with each other entirely. This creates a strange cosmic paradox. While dark matter continues to build and maintain galactic structures on smaller scales, dark energy is simultaneously working to isolate these structures from each other on larger scales. It's as if the universe is both growing more organized and more fragmented at the same time. The nature of dark energy remains even more mysterious than dark matter. While we have specific particle candidates for dark matter and experiments designed to detect them, dark energy is much more elusive. It doesn't seem to be made of particles at all, but rather appears to be a property of space itself. The leading theoretical explanation is that dark energy represents the energy inherent in empty space, what physicists call vacuum energy. According to quantum mechanics, even empty space isn't truly empty, but is filled with virtual particles that pop into existence and annihilate each other in incredibly brief moments. This quantum foam should contribute a small amount of energy to every cubic meter of space. The problem is that when physicists calculate how much vacuum energy there should be, they get an answer that's either zero or catastrophically large, depending on the assumptions they make. The amount of dark energy we actually observe is tiny by comparison, but not zero. This mismatch between theory and observation is one of the most significant unsolved problems in physics. Alternative theories suggest that dark energy might not be constant after all, but could change over time. Perhaps it's associated with a slowly evolving field that permeates all of space, similar to the field thought to drive cosmic inflation in the very early universe. These models predict that dark energy strength might increase or decrease as the universe ages, potentially leading to very different cosmic futures than those predicted by a constant dark energy. Some physicists have even suggested that dark energy might be an illusion, a sign that our understanding of gravity breaks down on the largest scales. Just as modified gravity theories attempt to explain dark matter without invoking new particles, modified gravity might also account for cosmic acceleration without requiring dark energy. But the observational evidence for dark energy is remarkably consistent across multiple independent measurements. The cosmic microwave background radiation shows the geometric signature of a flat universe with the energy budget dominated by dark energy. Observations of distant supernovae continue to map out the expansion history of the universe in exquisite detail. Large-scale surveys of galaxy distributions reveal the effects of dark energy on structure formation over cosmic time. As we peer into the future, the ongoing battle between dark matter and dark energy will determine the ultimate fate of everything we see. If dark energy remains constant, as current observations suggest, then cosmic expansion will continue to accelerate forever. Galaxies outside our local group will eventually recede so fast that their light will be redshifted beyond detection. The cosmic microwave background will cool and fade until it becomes undetectable. In this scenario, the universe will enter what cosmologists call the heat death, a state of maximum entropy where energy is spread so thinly that no new structures can form and no useful work can be done. Stars will continue to shine until they exhaust their fuel, but no new stars will form as the gas needed for star formation becomes too diffuse to collapse under its own gravity. Eventually, even the protons that make up atomic nuclei may decay, leaving behind only electrons, positrons, and photons in an ever-expanding, ever-cooling cosmos. Black holes will slowly evaporate through Hawking radiation, taking trillions upon trillions of years to completely disappear. In the end, the universe will be a cold, dark, empty expanse, with only the faintest traces of radiation marking where galaxies once shone. But this far future remains uncertain. We don't know if dark energy will remain constant forever, or if it might change in ways that could alter the universe's destiny. Perhaps dark energy will decay or transform into something else, allowing gravity and dark matter to regain dominance and begin pulling the universe back together in a big crunch. Or perhaps the acceleration will increase, leading to a big rip, where dark energy becomes so powerful that it overcomes not just gravity on cosmic scales, but all the fundamental forces that hold atoms and even subatomic particles together. In this scenario, the universe would end not in cold emptiness, but in a moment of infinite expansion that tears apart the very fabric of reality itself. For now, though, we exist in a remarkable epoch of cosmic history. Dark matter has had enough time to build the magnificent structures we see around us, galaxies and clusters and the vast cosmic web that connects them all. Dark energy has begun to dominate, but hasn't yet had time to completely isolate these structures from each other. We live in a universe that is both richly structured and dynamically evolving, caught between the constructive influence of dark matter and the dispersive power of dark energy. This cosmic dance between invisible forces continues all around us, mostly unnoticed in our daily lives but fundamental to everything we are and everything we see. Every star that shines, every planet that orbits, every galaxy that spirals through the night sky exists because of this delicate balance between attraction and expansion, between the patient construction work of dark matter and the relentless stretching of space itself. As you drift off to sleep tonight, you might imagine yourself floating gently through this invisible cosmic architecture, surrounded by the dark matter that helped create our galaxy, carried along by the dark energy that shapes our universe's future. These forces are as real as gravity, as fundamental as electromagnetism, yet they remain largely hidden from our direct perception, working their quiet magic in the darkness between the stars. The story of dark matter and dark energy is still being written, each new observation adding another piece to the cosmic puzzle. But already, this tale of invisible forces has transformed our understanding of the universe and our place within it. We are not just made of star stuff, as Carl Sagan famously said. We are embedded in a cosmic web of dark matter, carried along by the expansion of space itself, witnesses to a universe far stranger and more wonderful than our ancestors ever imagined. In this vast cosmic symphony, dark matter serves as both composer and conductor, orchestrating the formation of structures across scales we can barely comprehend. But to truly appreciate its role as the universe's architect, we need to zoom in from the cosmic web and focus on how this invisible scaffolding operates within individual galaxies, shaping not just their formation, but their ongoing evolution over billions of years. Consider the Milky Way, our home galaxy, as it exists today. What you see when you look up at the night sky represents only the tip of an enormous iceberg. The familiar band of starlight stretching across the heavens marks just the inner regions of a vast dark matter halo that extends far beyond the visible edges of our galaxy. This halo isn't uniform or static. It's a complex, dynamic structure with its own geography of density peaks and valleys, substructures and streams, all invisible to our eyes yet fundamental to our galaxy's very existence. Within this dark matter framework, ordinary matter follows patterns that would be impossible without the invisible scaffolding. The spiral arms that give galaxies like ours their distinctive appearance aren't permanent features carved in stone. They're density waves that propagate through the galactic disk like ripples on a cosmic pond. These waves are sustained by the gravitational interactions between the visible matter in the disk and the extended dark matter halo that surrounds it. As stars orbit the galactic center, they occasionally enter and exit these spiral arms, spending perhaps 10 million years within an arm before moving back into the quieter regions between. During their passage through the arms, stars encounter higher densities of gas and dust, triggering new episodes of star formation. The newborn stars illuminate the spiral pattern, making it visible to observers like us. but the pattern itself is maintained by the dark matter's gravitational influence. This process creates a kind of cosmic recycling system. Massive stars born in the spiral arms live fast and die young, exploding as supernovae that scatter heavy elements throughout the galaxy. These elements mix with the primordial hydrogen and helium, enriching the gas that will form future generations of stars. Over billions of years, this cycle has gradually increased the metallicity of our galaxy, creating the chemical diversity necessary for rocky planets and, ultimately, life itself. But dark matter's influence extends beyond maintaining spiral structure. It also regulates the pace at which galaxies consume their gas reserves. Without the stabilizing presence of a dark matter halo, the energy released by massive stars and stellar explosions would blow most of a galaxy's gas into intergalactic space, effectively shutting down star formation after just a few 100 million years. Instead, the dark matter halo acts like a gravitational reservoir, capturing much of this heated gas and allowing it to cool and settle back into the galactic disk over time. This creates what astronomers call a galactic fountain, where gas is constantly cycling between the disk, where stars form, and the halo, where it cools and rains back down to fuel future star formation. This fountain effect helps explain why galaxies can maintain steady rates of star formation for billions of years rather than exhausting their fuel supplies in a single burst of activity. The Milky Way has been forming stars for more than 10 billion years, creating multiple generations of stellar populations, each one slightly more enriched with heavy elements than the last. This wouldn't be possible without the moderating influence of our galaxy's dark matter halo. The relationship between dark matter and star formation becomes even more complex when we consider the role of supermassive black holes. Nearly every large galaxy harbors one of these monsters at its center, with masses millions or billions of times greater than our Sun. The black hole at the center of the Milky Way, known as Sagittarius A star, contains about 4 million solar masses compressed into a region smaller than our solar system. These supermassive black holes didn't form randomly. Their growth is intimately connected to the assembly history of their host galaxies' dark matter halos. As dark matter halos merge and grow, they bring together smaller black holes from their constituent galaxies. These black holes eventually spiral toward the center of the merged system, where they can combine to form even more massive black holes. But supermassive black holes do more than simply grow along with their host galaxies. They actively regulate star formation through a process called feedback. When gas falls toward a supermassive black hole, it forms an accretion disk that can become incredibly hot and luminous. This creates powerful outflows of radiation and particles that heat the surrounding gas, preventing it from cooling and collapsing to form new stars. This feedback mechanism creates a delicate balance. If the black hole is too active, it can shut down star formation entirely, leading to a red dead galaxy populated only by old stars. If it's not active enough, star formation can proceed unchecked, rapidly exhausting the galaxy's gas supply. The sweet spot produces galaxies like our own, where star formation continues at a sustainable rate for billions of years. The dark matter halo plays a crucial role in this process by providing the gravitational framework that determines how gas flows toward the galactic center and how effectively black hole feedback can regulate star formation. In smaller dark matter halos, feedback can more easily blow gas out of the galaxy entirely. In larger halos, the deeper gravitational well can retain gas even in the face of powerful black hole outflows. This creates a natural sorting mechanism where galaxies of different masses end up with very different properties. The most massive galaxies, embedded in the most massive dark matter halos, tend to be large, red ellipticals with little ongoing star formation. Intermediate mass galaxies like the Milky Way maintain spiral structure and steady star formation. The smallest galaxies often appear as irregular, star-forming systems with very little structure. But dark matter's architectural influence operates on scales both larger and smaller than individual galaxies. On larger scales, it creates the cosmic web that channels matter along filaments toward the nodes where galaxy clusters form. On smaller scales, it may be responsible for the existence of the dark matter substructures that we observe as satellite galaxies orbiting larger systems. The Milky Way is surrounded by dozens of these satellite galaxies, ranging from the relatively large Magellanic Clouds, visible to the naked eye from southern latitudes, to tiny, ultra-faint dwarfs that contain only a few thousand stars. Each of these satellites sits within its own dark matter subhalo, a smaller structure that survived the tidal forces encountered during its infall toward our galaxy. These satellite systems provide some of our best laboratories for studying dark matter's properties. Because they're so small and contain so few stars, their dynamics are dominated by dark matter to an even greater degree than larger galaxies. By measuring the motions of stars within these satellites, astronomers can map their dark matter content with remarkable precision. What they find consistently surprises them. Many of these satellite galaxies appear to contain far more dark matter than theoretical models predict. Some are so dark matter dominated that they challenge our understanding of how galaxies form and evolve. These observations have led to ongoing debates about the nature of dark matter and whether our current models accurately capture its behavior on the smallest scales. The most extreme examples are the so-called dark galaxies, systems that may contain substantial amounts of dark matter, but very few or even no visible stars at all. These ghostly structures would be essentially invisible except for their gravitational effects on nearby systems. If they exist in large numbers, they could represent a hidden population of dark matter halos that never managed to form significant stellar populations. Detecting and studying these dark galaxies requires extraordinary observational techniques. Astronomers look for gravitational lensing effects, where the dark matter in these systems bends light from more distant objects. They search for tidal streams, trails of stars stripped from satellite galaxies, as they orbit within the Milky Way's dark matter halo. They even use the motions of visible satellites to infer the presence of invisible structures that might be perturbing their orbits. Each of these techniques adds another piece to our growing map of the dark matter distribution around our galaxy. What emerges is a picture of incredible complexity, with substructures nested within larger structures in a hierarchical pattern that extends down to the smallest scales we can observe. This hierarchical structure reflects the bottom-up nature of galaxy formation in a dark matter-dominated universe. Small dark matter halos form first, then merge to build larger structures in a process that continues today. Some of these mergers are gentle, allowing satellite galaxies to survive as distinct entities within larger halos. Others are violent disruptions that tear apart the smaller system and scatter its stars and dark matter throughout the larger galaxy. The Milky Way itself bears the scars of these ancient mergers. Stellar streams crisscross our galaxy's halo, marking the orbital paths of satellite galaxies that were disrupted millions or billions of years ago. The thick disk component of our galaxy may represent the remnant of a major merger that occurred early in the Milky Way's history, when a substantial satellite galaxy was completely absorbed and its stars scattered throughout our galactic disk. These merger events don't just add mass to galaxies. They also trigger bursts of star formation, shake up existing stellar populations, and can completely reshape a galaxy's morphology. A spiral galaxy can be transformed into an elliptical through a major merger, while minor mergers might create features like stellar shells, tidal tails, or warped disks. The frequency and timing of these merger events is determined by the assembly history of dark matter halos, which in turn depends on the initial conditions set down in the very early universe. The tiny density fluctuations present just after the Big Bang have grown and evolved over billions of years, guided by dark matter's gravitational influence, to create the rich tapestry of galactic structures we observe today. But this cosmic construction project is far from complete. Dark matter continues to build and reshape galaxies even now, billions of years after the first structures formed. New satellite galaxies are still being accreted by the Milky Way, bringing with them their own dark matter subhalos. The large and small Magellanic Clouds, our nearest galactic neighbors, are currently in the process of being tidally disrupted, creating streams of gas and stars that will eventually rain down onto our galactic disk. At the same time, our local group of galaxies is slowly collapsing under its own gravity. In about 4 billion years, the Milky Way and the Andromeda Galaxy will collide and merge, creating a new elliptical galaxy that astronomers have playfully dubbed Milkomeda. This future merger will be orchestrated by the dark matter halos of both galaxies, which will merge first, creating the gravitational framework within which the stellar populations will eventually settle. Even after this dramatic collision, the story won't end. The merged system will continue to accrete smaller galaxies from the surrounding region, gradually growing in mass and complexity. But as the universe continues to expand and dark energy becomes increasingly dominant, these merger events will become rarer and more widely separated in time. Eventually, the local group will become increasingly isolated from the rest of the universe as cosmic expansion carries distant galaxies beyond our gravitational reach. We'll be left with a single, massive elliptical galaxy embedded in a vast dark matter halo, surrounded by the growing emptiness of an accelerating universe. But that's still billions of years in the future. For now, we exist in a remarkably active phase of cosmic evolution, where dark matter continues to shape and reshape the galactic structures around us. Every night, as you gaze up at the stars, you're looking at the visible manifestation of an invisible architecture that has been under construction for over 13 billion years. The spiral arms of the Milky Way, traced out in the soft glow of distant stars, are temporary patterns in a dance choreographed by dark matter. The satellite galaxies scattered around our cosmic neighborhood are the surviving fragments of ancient accretion events, each one a testament to dark matter's patient work of assembly. Even the chemical elements that make up your body were forged in stars whose formation was regulated by dark matter's invisible influence. This is the true legacy of dark matter as the universe's architect. It doesn't build with dramatic flourishes or sudden revelations, but with the slow, steady persistence of gravity acting over cosmic time. Particle by particle, star by star, galaxy by galaxy, it has constructed the framework within which all the beauty and complexity of the cosmos can unfold. As we continue to unravel the mysteries of dark matter through increasingly sophisticated observations and experiments, we're not just learning about an invisible component of the universe. We're discovering the hidden blueprints that guided the construction of everything we see. The secret history of cosmic architecture written in the language of gravity itself. In our final exploration, we'll discover how this cosmic mystery continues to evolve, as dark matter and ordinary matter engage in an eternal dance that shapes not just the galaxies we see today, but the cosmic structures that will emerge in the distant future, in a universe where darkness itself has become the foundation for all light. The dance between dark matter and ordinary matter continues to unfold in ways that still surprise astronomers, revealing new layers of complexity in this cosmic partnership. As we peer deeper into space with ever more sophisticated instruments, we're discovering that the relationship between these two fundamental components of our universe is far more intricate and dynamic than we ever imagined. Consider what happens when galaxies encounter each other in the vast emptiness of space. These cosmic meetings aren't rare events relegated to the distant past. They're happening all around us all the time, though on timescales so vast that entire civilizations could rise and fall between the opening act and final curtain of a single galactic encounter. When two galaxies begin their gravitational waltz, it's their dark matter halos that lead the dance. These invisible structures, extending far beyond the visible boundaries of their galaxies, begin to interact long before the stars themselves come into play. The halos stretch toward each other like cosmic tentacles, their gravitational fields probing and testing, creating tidal forces that can be felt across millions of light years. As the encounter progresses, the dark matter halos begin to merge in a process that's both violent and graceful. Unlike the stars and gas within the galaxies, which can collide and interact through electromagnetic forces, dark matter particles simply pass through each other like ghosts in the night. This creates a fascinating separation of behaviors during galactic collisions, where the dark matter and ordinary matter can actually become temporarily disconnected from each other. Imagine watching a cosmic magic trick where the invisible framework of one galaxy slides seamlessly through another, while the visible stars and gas clouds are swept up in complex gravitational currents, some being flung out into intergalactic space, others compressed into dense knots that trigger explosive bursts of new star formation. The dark matter, meanwhile, continues its silent journey, eventually settling into a new configuration that will determine the final structure of the merged system. This process has been captured in exquisite detail by computer simulations that track billions of particles over cosmic time. These digital universes reveal dark matter's role as both destroyer and creator. During galaxy mergers, it can disrupt existing structures, tearing apart spiral arms and scattering stellar populations. But it also provides the gravitational foundation for new structures to emerge from the chaos. The simulations show how dark matter streams flow like invisible rivers through the cosmos, carrying ordinary matter along predetermined channels toward regions where new galaxies will eventually form. These streams aren't uniform or predictable. They branch and merge, creating a complex network of gravitational highways that guide matter across billions of light years of space. Some of these streams are so substantial that they can be detected observationally, not through the dark matter itself, but through the ordinary matter they carry along. Astronomers have discovered vast filaments of hydrogen gas stretching between galaxies, glowing faintly in the light of distant quasars. These gas filaments trace out the dark matter scaffolding that underlies the cosmic web, making visible the otherwise invisible architecture of the universe. But dark matter's influence extends beyond these grand cosmic structures. It shapes the internal architecture of galaxies in ways that are only now being understood. Within the Milky Way, for instance, dark matter doesn't form a smooth, uniform halo. Instead, it's full of substructures, clumps and streams and shells of varying density that reflect the complex history of our galaxy's assembly. Some of these substructures are the remnants of smaller dark matter halos that were consumed during the Milky Way's growth. As satellite galaxies fall into our galaxy's gravitational well, their dark matter halos are gradually torn apart by tidal forces. But the dark matter doesn't simply disappear or distribute itself evenly. Instead, it forms long, coherent streams that orbit within the larger halo like ghostly rivers flowing through an invisible landscape. These dark matter streams can persist for billions of years, maintaining their structure even as they're stretched and distorted by the galaxy's gravitational field. They create a kind of fossil record of galactic assembly, preserving information about merger events that occurred long ago. By mapping these streams, astronomers can reconstruct the history of our galaxy's growth, identifying which satellite galaxies were accreted, when, and from which directions they approached. The discovery of these substructures has profound implications for our understanding of dark matter's properties. The fact that streams can maintain their coherence for so long tells us something important about how weakly dark matter particles interact with each other. If they collided frequently or radiated energy efficiently, these streams would dissipate quickly, their structure smoothed away by countless microscopic interactions. But the streams persist, ghostly highways of invisible matter threading through our galaxy's halo, carrying with them the memory of cosmic construction projects that began billions of years ago. They're a reminder that dark matter isn't just a passive scaffolding, but an active participant in the ongoing evolution of galactic structures. This dynamic nature of dark matter becomes even more apparent when we consider how it responds to the ordinary matter it shepherds. As stars form within dark matter halos, they don't just passively inhabit the gravitational wells their invisible hosts provide. The energy they release through stellar winds and supernova explosions creates feedback that can actually reshape the dark matter distribution itself. In the smallest galaxies, this feedback can be particularly dramatic. The explosion of just a few massive stars can blow so much energy into the surrounding dark matter halo that it actually expands, becoming less dense and less centrally concentrated. This creates a complex interplay where the ordinary matter, despite being vastly outnumbered by dark matter, can actually influence the structure of its invisible host. These feedback processes help explain one of the most puzzling observations in galaxy formation theory. Computer simulations predict that dark matter halos should have very steep density profiles, with much more dark matter concentrated near their centers than observations actually show. The energy injection from star formation appears to solve this problem, puffing up the inner regions of dark matter halos and creating the flatter density profiles that astronomers observe. This mutual influence between dark and ordinary matter extends to larger scales as well. The formation of massive galaxy clusters, the largest gravitationally bound structures in the universe, involves a complex choreography between these two components. As smaller groups and individual galaxies fall into the growing cluster, their dark matter halos merge and virialize, creating the deep, gravitational potential well that defines the cluster's structure. But the ordinary matter follows a different path. Much of it exists as hot gas in the space between galaxies, heated to temperatures of millions of degrees by the violent processes of structure formation. This gas can be observed through its X-ray emission, creating luminous halos around galaxy clusters that trace out the distribution of ordinary matter in these systems. The relationship between the X-ray emitting gas and the underlying dark matter distribution provides one of our most powerful tools for studying dark matter's properties. During cluster collisions, these two components can become spatially separated, with the gas being slowed by electromagnetic interactions, while the dark matter passes through relatively unimpeded. This creates dramatic examples of dark matter's nearly collisionless nature, providing some of our strongest evidence that dark matter truly exists as a distinct physical component rather than simply representing a modification of gravitational physics. These cluster collision events are like cosmic particle accelerators, creating conditions that reveal fundamental properties of dark matter that would be difficult to study any other way. They show us that dark matter interactions, if they exist at all beyond gravity, must be extraordinarily weak. They demonstrate that dark matter can be separated from ordinary matter, behaving as an independent fluid governed primarily by gravitational forces. But perhaps most importantly, these observations reveal dark matter's role as the universe's primary structural engineer. In every cluster collision, it's the dark matter that determines the final configuration of the merged system. The ordinary matter, despite being more visible and more easily observed, is essentially along for the ride, following the gravitational roadmap laid out by its invisible partner. This asymmetric partnership extends to the formation of the cosmic web itself. The vast network of filaments and nodes that spans the observable universe is primarily a dark matter phenomenon. Ordinary matter simply follows the gravitational channels that dark matter has carved out, flowing along predetermined paths toward regions where galaxies and galaxy clusters will eventually form. The cosmic web isn't static, though. It continues to evolve as the universe expands and ages, with dark matter streams constantly flowing along its filaments, carrying ordinary matter toward ever larger structures. This ongoing construction project operates on timescales so vast that the human mind can barely comprehend them. Yet it proceeds with mechanical precision, following the inexorable pull of gravity across cosmic distances. As we look toward the future, this construction project faces an uncertain fate. The accelerating expansion of space, driven by dark energy, is gradually diluting the cosmic web, stretching its filaments and isolating its nodes. The streams of dark matter that have been building galactic structures for billions of years are being stretched thinner and thinner, their ability to deliver new material to growing galaxies gradually diminishing. In the distant future, these streams may be stretched beyond their ability to maintain coherence, effectively shutting down the supply of new material to galaxies. Star formation will gradually wind down as existing gas supplies are exhausted and no new material arrives to replenish them. The universe will enter a new phase where the structures built by dark matter during the first few billion years after the Big Bang represent the final architectural achievement of cosmic construction. But that future lies trillions of years ahead. For now, dark matter continues its patient work, building and reshaping the structures around us with the same quiet persistence it has shown for over 13 billion years. Every new star that forms, every galaxy that grows, every cluster that assembles represents another small victory for the invisible forces that have been shaping our universe since the very beginning. The story of dark matter as the universe's architect is ultimately a story about the hidden foundations that make complexity possible. Just as a cathedral's flying buttresses provide invisible support that allows soaring spires to reach toward the heavens, dark matter provides the gravitational framework that allows ordinary matter to organize itself into the rich tapestry of structures we see around us. Without this invisible foundation, the universe would be a much simpler, much emptier place. There would be no galaxies, no stars, no planets, and no observers like ourselves to contemplate the mystery of existence. The cosmos would remain forever smooth and featureless, a bland soup of particles expanding endlessly into an ever colder future. Instead, we find ourselves embedded in a universe of extraordinary richness and complexity, where invisible architects have been at work for billions of years, crafting the stage upon which all the drama of cosmic evolution unfolds. And as we continue to unravel the mysteries of dark matter through observation and experiment, we're not just learning about the invisible components of our universe, we're discovering the hidden blueprints that make our existence possible, the secret history written in the gravitational signatures of forces we cannot see but cannot live without. The dance between a dark matter and ordinary matter continues around us at every moment, mostly unnoticed, but fundamental to everything we are and everything we might become. It's a quiet reminder that the most important forces in the universe often work in darkness, shaping reality through patient persistence rather than dramatic display. And in that darkness, in that patient architectural work, lies one of the deepest truths about the cosmos we inhabit. Even now, as you listen to these words, dark matter streams are flowing through your body, through the room around you, through the Earth itself. Billions of dark matter particles are passing through every square centimeter of space each second, carrying with them the gravitational memory of structures that formed when the universe was young. You cannot feel them, cannot see them, cannot detect them with any instrument at your disposal. Yet they are there, silent witnesses to the cosmic construction project that made your existence possible. These particles have been traveling for billions of years, some of them set in motion by the gravitational collapse of the first dark matter halos, others stirred into motion by galaxy mergers that occurred when the universe was half its current age. They carry no information about their journey, no record of the structures they helped build or the cosmic events they witnessed. They simply flow, following trajectories determined by the large-scale gravitational field of the universe, part of a vast circulation system that connects every corner of the cosmos. The dark matter flowing through your location right now might have once been part of a satellite galaxy that was torn apart and absorbed by the Milky Way billions of years ago. Or it might belong to a smooth component of our galaxy's halo, particles that have been orbiting the galactic center for most of cosmic history, their paths gently perturbed by the gravitational influence of passing molecular clouds and stellar associations. Some of these particles might be part of more exotic structures, remnants of the very first objects to collapse in the early universe. These primordial dark matter halos would have been much denser and more compact than anything we see today, possibly dense enough to collapse into black holes or other exotic configurations. If such objects exist, They would represent fossil relics of the universe's infancy, preserved within the dark matter streams that flow through galaxies like ours. The thought of these invisible rivers flowing all around us might seem unsettling at first, but there's something deeply comforting about it as well. It means we're never truly isolated, never completely disconnected from the broader cosmic community. The same dark matter that flows through your body also flows through distant galaxies, creating invisible threads that connect every structure in the universe into a single, vast network. This connection operates on the most fundamental level possible, through gravity itself. The dark matter particle passing through your location at this moment exerts a tiny gravitational influence on every other particle in the observable universe. The effect is unimaginably small, far too weak to measure or feel, but it's real nonetheless. In some infinitesimal way, your presence affects the trajectory of dark matter particles throughout the cosmos, just as their passage affects you. These gravitational connections create a kind of cosmic democracy where every particle has a voice in determining the universe's future evolution. The dark matter flowing through Earth today will help determine where galaxies form in the distant future, which stars will ignite, which planetary systems will emerge from the cosmic darkness. It's a reminder that even the smallest components of the universe participate in the grandest stories of cosmic evolution. But dark matter's influence extends beyond these poetic connections to more practical considerations for the future of astronomy and cosmology. As our instruments become more sensitive and our theoretical understanding more sophisticated, we're beginning to detect subtler effects of dark matter's presence. Gravitational microlensing, the slight bending of light by dark matter clumps, can reveal individual dark matter structures within our own galaxy's halo. Future space missions will map the distribution of dark matter with unprecedented precision, creating three-dimensional charts of the invisible scaffolding that surrounds us. These maps will reveal the detailed structure of dark matter streams, the locations of ancient merger remnants, and perhaps even the signatures of dark matter self-interactions that current theories cannot predict. Ground-based experiments continue to push the boundaries of sensitivity, searching for the direct interaction of dark matter particles with ordinary matter. Deep underground laboratories, shielded from cosmic rays and other sources of interference, house detectors so sensitive they can register the collision of a single dark matter particle with an atomic nucleus. Each null result refines our understanding of dark matter's properties, gradually narrowing the range of possibilities for what these mysterious particles might be. The search for dark matter has also driven innovations in computational physics and data analysis. Simulating the formation and evolution of cosmic structures requires tracking billions or even trillions of particles over cosmic time, pushing supercomputers to their limits. The algorithms developed for these simulations have found applications in fields ranging from climate modeling to artificial intelligence, demonstrating how fundamental research in cosmology can yield unexpected practical benefits. Machine learning techniques originally developed for particle physics experiments are now being applied to astronomical surveys, automatically identifying galaxy clusters, measuring gravitational lensing signals, and discovering new types of cosmic structures. The same statistical methods used to search for dark matter in underground detectors help radiologists identify tumors in medical scans and help engineers optimize traffic flow in smart cities. This cross-pollination between dark matter research and other fields illustrates something profound about the nature of scientific inquiry. When we push the boundaries of human knowledge in any direction, we often discover connections and applications we never anticipated. The quest to understand dark matter isn't just about cosmology. It's about developing new ways of thinking about complex systems, new mathematical tools for analyzing vast datasets, new experimental techniques for detecting the barely detectable. As these techniques continue to improve, we may finally achieve the holy grail of dark matter research, direct detection of dark matter particles in laboratory experiments. Such a discovery would revolutionize our understanding of particle physics and cosmology simultaneously, opening new windows into the fundamental structure of reality. We would finally know what dark matter actually is, not just what it does. But even if direct detection remains elusive, the indirect evidence for dark matter continues to accumulate. Every new observation of galaxy rotation curves, every measurement of gravitational lensing, every map of the cosmic microwave background adds another piece to the puzzle. The consistency of these observations across such different scales and epochs creates a compelling case that we're observing the effects of a genuine cosmic component, not some systematic error in our understanding. The implications extend far beyond astronomy. If dark matter consists of new types of fundamental particles, it means our understanding of the basic building blocks of reality is incomplete. The standard model of particle physics, successful as it has been in describing the behavior of ordinary matter, represents only a small fraction of the universe's total inventory. There are entire categories of particles and forces waiting to be discovered, hidden realms of physics that could transform our technological capabilities in ways we can barely imagine. Perhaps dark matter particles could be harnessed as a new form of energy source, their interactions with specially designed detectors providing power for future spacecraft exploring the outer reaches of the solar system. Or maybe understanding dark matter physics will reveal new principles that revolutionize computing, communications, or transportation in ways that seem like science fiction today, but could become commonplace tomorrow. These speculative possibilities remind us that dark matter research isn't just an abstract intellectual exercise. It's an investment in humanity's future, an attempt to understand the universe well enough to navigate it successfully as our species expands beyond Earth. The invisible scaffolding that built our galaxy might, a cosmic enigma that challenges now, dark matter remains beautifully mysterious someday, provide the framework for our own expansion into the cosmic community. As we reach the end of our gentle journey through the invisible architecture of the cosmos, take a moment to marvel at the profound mystery that surrounds us. Dark matter, this silent cosmic sculptor, has been patiently building the universe for over 13 billion years, creating the gravitational scaffolding that allows stars to shine, planets to form, and life itself to emerge from the darkness. Every galaxy you see, every star that lights the night sky, every breath you take exists because of forces we cannot see but cannot live without. While dark matter continues to elude our direct detection, its fingerprints are written across the cosmos in the language of gravity itself. Perhaps that's the most beautiful part of this cosmic mystery, that the most important architect in the universe, Russ, works in complete silence, content to remain hidden while the structures it builds shine brilliantly for all to see. Sweet dreams, and remember that even in sleep, you're cradled within the invisible embrace of the universe's greatest construction project.